All right, let's get started. Okay, so the first module which we have discussed in the past 2 weeks is diodes and applications. Uh, in this topic, we have in this module we have a couple of topics that we have discussed, starting from diode operation. Uh, we started with diode operation, of course, and there is a voltage current characteristics of a PN junction diode. We don't have diode approximations. This is not considered in our syllabus. This topic doesn't have exist in the syllabus. Then applications of diode, we have half-wave rectifiers, full-wave rectifiers, then followed by power supply, filters, and regulators. So these are the topics that are covered under the module or chapter diodes and applications. This textbook also suggests to use software such as multisim and LT Spice so that you can simulate circuits using these two softwares, multi-sim and as well as or else LT Spice. Now files are provided with this each and every chapter so that student can install this. Multisim is a open source software and even LT Spice as well. You can download and you can install these to any one of these softwares and simulate the circuits which you come across on this course. Right. Then moving on to the objectives of the chapter, we have diode applications, then voltage current characteristics of the diode, the need to analyze, explain and analyze the operation of half-wave rectifier, full-wave rectifier, and power supply filters and regulators. So these were the objectives of this chapter. Then comes, if we move on to the introductory section, we need to understand the operation and characteristics of the diode that is covered in this chapter. We should know how the diode conduct, its ability to conduct current in one direction while blocking current in the other direction is essentially the uh, operation of many types of circuits. One such is going to be the diode, which works on this basis. Uh, Diodes are also used in rectifier circuits, which where we need to convert AC signal to DC. We use a PN junction or diode. Okay, so these are the major applications of PN junction. And before we proceed to the chapter, we need to understand what do we mean by diode or PN junction. This is also called as a diode or PN junction. It has a P and N type semiconductor which forms the PN junction, which allows the current to conduct in one direction. Bias in the sense need to apply some voltage to the PN junction so that the diode conducts. That application of voltage is called as bias. When we say application of voltage, we can apply voltage in different directions. uh, Connecting P type of semiconductor in the diode to the positive and N type semiconductor to the negative is called as a forward bias. And oppositely, if you connect it, P type semiconductor of diode to the negative terminal of battery and N type semiconductor to the positive terminal of the battery, then it is called reverse bias. And we should see the effect of forward and reverse bias with the help of the characteristics called as voltage current characteristics. And we need to study how to design a DC direct current power supply, which consists of various sub blocks. The major or basic element in this DC power supply is the diode. Within the DC power supply, we have a circuit called as a rectifier. A first block, after transformer is the rectifier circuit. Then comes a filter, because the rectifier cannot convert the fully AC voltage to DC voltage. So we need to use a filter circuit. Filter circuit, a partial amount of AC exists even after filtering the rectified output. Therefore, we need to have a regulator. Okay, a regulator which smoothens the filter output. That's how the regulator performs. Then comes halfwave rectifier. Uh, Halfwave rectifier is again a part of a DC power supply. As we said already, rectifier has got two important types. One is half-wave rectifier, other one is going to be the full-wave rectifier. One of the important characteristics of rectifier is the peak inverse voltage. How much the reverse voltage a diode can withstand in a rectifier. That is often defined as peak inverse voltage. Then comes ripple voltage is also important. Ripple is nothing but an AC voltage. Once you convert AC to DC, okay, the DC voltage, the DC signal here may not be 100% DC. It contains some amount of ripple in the sense which is an AC component in the DC. So we need to have a small amount of ripple, but DC. But if you look at output of a rectifier, we will have a ripple percentage is higher. But as we move from regulator rectifier to the filter, the amount of ripple keeps reducing. Then the two performance measurements of regulations are line regulations and load regulations. We need to calculate these two regulations with reference to the regulator topic. So these are the various key terms and definitions one need to be aware before we start discussing the different applications of PN junction. So we have highlighted important points under each section. The students can go through these things, and if they have any questions, they can also ask. First and foremost is, let us look at the diode operation here. What is diode? Diode is nothing but it is also called as a PN junction. Diode or PN junction is same, they're not different. Okay, it's a two-terminal semiconductor device. This junction, PN junction or diode, is a two-terminal semiconductor device formed by two doped regions of silicon, which is separated by a PN junction. There are two junctions in this, two types of semiconductors in this. One is P type, another one is going to be the N type, and this forms a junction in between them, and the entire device is called as a diode. And there are two terminals attached to this PN junction. So one is the anode, other one is going to be the cathode. And where different types of diodes exist, and here what we are discussing is going to be the general purpose diode. Ordinary diode are also called as general purpose diode. Other types of diodes are, you can see the rectifier diodes exist, which have different specifications, and even signal diodes also exist, that also comes with different specifications, commonly used in communication circuits, and those are called as signal diodes. Even while clipping, clamping, in order to remove the certain portion of unwanted signal, we can use diode or PN junction. Okay, so there are variety of applications of PN junctions. So in this chapter, you are going to learn how to use a voltage to make the diode to conduct current in one direction and block the current in other direction. And this allowing the current in one direction and blocking the current in other direction, this entire process is also called as biasing. I hope you got the definition of the biasing. Applying the voltage, suitable voltage to the PN junction, if you apply in one direction, that will allow the current to flow, and the other type of voltage, if you change the voltage, it may block the current in other direction. And this application of voltage, in a proper way, is called as the biasing. So once you complete this chapter, you will be in a position to understand the the symbolic representation of a diode, and I will show that later on, and how diodes are manufactured, different types of packages of which diodes are manufactured. Those things we are going to look at, and the different types of bias that we apply, forward bias and reverse bias, namely. Okay, that we'll discuss in detail. Here we just explained what do we mean by bias, but later on we are going to explain in detail how to forward bias the PN junction or diode, and how to reverse bias the PN junction or diode, and what are the currents that flow in the forward bias diode. Those things also we will discuss, and what are the impact of the changes in the semiconductor when we apply the forward bias diode, especially the barrier potential, a depletion region, how it changes when we apply the forward bias, and how the depletion region varies, increases when you apply the reverse bias, and the current that is flowing in the reverse direction. And once you apply excess voltage in the reverse direction, how that causes the breakdown. All those things we are going to discuss in this chapter. Okay, let's now look at the diode, how it looks. As we already defined the definition of a diode is made up of small piece of semiconductor material, and it's usually silicon. Whether it's a P type or N type, it doesn't matter. The complete material is of silicon. In that, half of the portion is of P region, half it is doped with a P region. When we take entire bulk of silicon material, one side we dope with P type of, trivalent impurity region that forms the P type semiconductor, and other side when you dope with pentavalent impurity elements. This is trivalent, the foreign elements which have three valence electrons in the valence band. So such type of metal, if you dope it to the pure silicon, so it becomes a P type, and the other side it becomes an N type, and that's what it is explained here. Half is doped as an N region, and half of that is doped as a P region, with a PN junction in between these two P and N type regions. A junction is formed. This is a white portion. What you are seeing is going to be the junction, okay, which we call as a depletion region between those two. The reason why we call as a depletion, because there are no charge carriers in this region. Okay, so that's why it is, charges have been depleted. That's why it is called depletion region. And the P region is called the anode. So we attach a terminal to this P region, and that is called as an anode here. That's what you are seeing. And when we attach a terminal to the N region, that is called as a cathode. Okay, so these are the two electrodes taken from each type of semiconductor. Accordingly, it is called as anode and cathode. Okay, that's why this device is called a diode. Di means it is a two. There are two electrodes in this. Okay, so that's the name. That's how the name has come as a diode. Okay. All right. So this complete material is a semiconductor material, and we have converted impure semiconductor silicon intrinsic semiconductor into the P region and the N region, and that forms the depletion region. Okay, or junction, what we call junction is a middle part in a low portion. What you see is a junction, which is an interface of P type and N type semiconductor, and then later on we attach a metal lens to this, called namely as anode and cathode. Okay, then comes this is how the diode is made up of. Okay, this is how the structure of internal structure of a PN junction looks like. This is called as a basic structure, and many times we can't write this structure in while writing the circuits. We need to come out with a symbol, standard symbol. So standard symbol is an arrow mark with a vertical line here. Okay, so something like this. We have an arrow mark, and there is a vertical line that represents a diode. Vertical line indicates current is not permitted in this way. Okay, so current only is permitted in the forward direction. When you bias in the forward direction, then only the current is permitted. This is not allowed. That's why the vertical line here has been shown. From cathode to anode, current is not allowed, and the current flows from anode to cathode. And the symbol is an arrow symbol with a vertical line. That is the standard symbol of a PN junction. So this junction, what you are seeing here, the structure for that. So we have arrived at a symbolic representation of it. Okay. Then comes how these PN junctions are manufactured. How, because the silicon, what I mentioned, P and N type semiconductor, and we need to encapsulate this entire region in a package, and that comes in two different way. One is diode pack, typical diode packages, which has got two terminals, which is anode and cathode. Okay, and generally this comes in normal okay, the package, a plastic or ceramic type of package. uh, on those package, the cathode and the anode terminals are indicated here. Generally we indicate the cathode, and the other terminal anode is understood. Okay, then comes other standard packages, like the surface mount diode package, uh, that's called the SMA package. Okay, assembly. SMA means a surface mount assembly. Okay, so it also comes in different types of the mountings. Okay, so SOD type of mounting and SOT type of mounting. Okay, these are different packages which are available, and this SOD and SOT packages are of the shape of galving type of the shape. Okay, whereas SMA package has L-shaped LEDs. Okay, we'll show the diagram representation of these different packages. The SOD and SMA types have a band on one end of to indicate it is a cathode, and the other one, it is understood it is an anode. SOT type is a three-terminal package in which either one of them, one or two, okay, diodes are placed inside that. And SOT can be of a single diode, or SOT can be of uh, dual diode type package. Also, it comes within a single package. You can see two diodes. And it can also be manufactured with single diode also. That's how the different packages are manufactured. Okay. So the expansion of this I've discussed in the class as well. I'll just show you for your reference. Okay, so how these packages are labeled. Okay, so SOD stands for small outline diode. SOT stands as small outline transistor, though it is a package for a diode. Traditionally, the name was given as SOT. So even for diode, we use SOT as a package standard. And SMA, we already said that it is a surface mount assembly. And the diodes are named in the way like DO 214, and this is an SMA standard. Okay, so this is the code given by the manufacturer, 214. So for the different type of devices what they manufacture. Okay, all right, that's the different packages as you can see here. So these are the same thing that we have discussed. Diodes comes in different packages like anode, cathode, and different styles. It comes like this. You can see here DO21, and this again another type of package. See here, and again here. Okay, and SOD packages also has been shown here. SOT packages also shown here. Okay, so these are the different ways the diodes are packaged in a sealed manner. With that, let me move to the forward bias. Okay, so forward bias is basically the allowing the PN junction to conduct. To bias a diode, we need to apply a DC voltage. We will see what happens when you apply AC voltage to the diode in the next topic that we are going to discuss. Forward bias is the condition that allow the current through the PN junction. So this always when you bias in the forward direction, it allows the current to flow through the PN junction. Okay, so this is a diagram which shows how to connect a diode in the forward direction. So this diagram shows a diode connected for forward bias. Okay, look at here. There is a battery here, DC voltage. So this is the DC uh, voltage. Okay, which is a variable voltage, which is connected positive, because DC voltage has got polarities, positive and negative. The DC voltage is labeled as V bias. Okay, so bias means it's voltage. It's a name given to the DC voltage is V bias. V stands for voltage and bias stands for the voltage that is applied for the PN junction. It's just a naming. And here we have a resistor here. A typical resistor is less than 1K can be used here to limit the current surge to the PN junction. Okay, the value is not mentioned here, so small value of a small resistor can be used here, and the importance of that is shown here. The external bias voltage is designated as V bias. The resistor limits the forward current to a value that will not damage the diode. So in order to avoid damage of diode, we need to have a resistor that is shown here, R limit. It's a current limiting resistor. And the negative side of the V bias is connected to the N region of the diode. You can see that the negative side here of a DC voltage or V bias is connected to the N region of the diode. Okay, and the positive side of a V bias is connected to the P region via this resistor is connected to the P region of the diode. And this is a requirement for the diode to forward bias. When we say diode is forward bias, this is a sort of connection that we need to have for the PN junction or diode. Okay, V bias connected to the positive of V bias connected to the P type of semiconductor, and the negative of bias voltage connected to the N type of semiconductor. If you connect it in this way through the with the help of a current limiting resistor, then we say that the diode is forward biased. Okay, and the second requirement is the voltage what we apply here, the bias voltage. The question is, what should be the magnitude of this voltage here that we are connected here, and that must be greater enough to overcome the barrier potential here, so which we call VB here, as we already said that in the beginning. So between the P and N junction, there exists a barrier potential, which is typically a voltage is developed, inbuilt voltage of 0.7 volt is developed at equilibrium. So now this voltage V bias that we apply, that must be greater than this, otherwise device won't conduct. Okay, so this is labeled as VB. It is mentioned in the last line, you can see here. After connecting this diode in the forward bias, we must ensure that V bias is greater than VB. So otherwise device will not conduct. Like right here, V bias voltage, that is the bias voltage, must be greater than VB. VB is nothing but it is the barrier potential which exists within the diode, which is typically it is 0.7 volts for silicon diode. Okay. That is the fundamental operation of diode in the forward direction. And now let us see what happens when we apply voltage here in the forward direction. Without applying voltage, what happens? Once we apply the voltage, what happens? That we are going to see in this following topics. We know that like charges repel each other. There are two types of charges, holes and holes. They repel each other. Electrons, they repel each other. But there are chances of attraction of electron to hole and a hole with the electron. Okay, unlike charges attract, like charges repel each other. So here let us see that P-type, the majority charge carriers are the holes, and we should see even the minority charge carriers. Here the majority charge carriers are holes and the minority charge carriers are electrons. So they are minority, and here holes are majority. However, in the N region, it is just an opposite. Electrons are the majority charge carriers, whereas holes are the minority charge carriers. So in an N-type or P-type semiconductor, there existed two types of charge carriers. In a P-type, holes are majority, electrons are minority. In N-type semiconductor, electrons are majority, holes are minority charge carriers. So to understand the current flow in a semiconductor material, we should know how this electron hole movement happens in the P-type and similarly in the N-type, so that you understand entire current flow in the semiconductor. The negative side of the V bias voltage source pushes the free electrons, which are majority charge carriers in the N region, toward the PN junction. This flow of free electrons is called electron current. What we are trying to say here, since as we said already, the N-type, the majority charge carriers are electrons, and you see here the negative side of the bias voltage and the electron, there are like charges, right? And therefore the like charges, what we said here, they repel each other. Therefore electrons cannot move in this to the power supply. Instead they move towards the junction, towards the PN junction. The electron movement is like this. Electron C starts from the supply and they move towards the junction, PN junction. And now when we say electrons are moving, then that means the electron current exists. When electrons keep moving, electron current exists. Okay, that's what we are trying to say in this one. And the opposite happens in the P side. Whatever we say to the N side, the opposite happens in the P side here. The bias voltage source imparts a sufficient energy to the free electrons for them to overcome the barrier potential of the depletion region and move on through into the P region. What we are trying to say is the electrons will be moving to the PN junction, towards the PN junction. A lot of electrons are supplied by the negative terminal of a battery, and there are too many electrons. Now these electrons, whatever we are providing here, that must overcome the barrier potential of 0.7 volts in the junction, and once they overcome, they go and reach the P region. And here subsequent motion of the electrons, because here the holes are repelled by this, and holes will move in opposite way, but electrons, they move towards the positive terminal of a battery. So in a simple way, I should say here, electrons get attracted, they get repelled by this battery and keep moving towards the junction, and in turn they attracted to the positive terminal of a battery and reach the positive of a battery, and this causes the electron movement from N side to the P side. Hole movement happens oppositely. It's from P side to the N side, and current flows from P to N. When we say electron flows from N to P, this is the electron direction. They reach the positive of a terminal of a battery. This is electron flow. So naturally the current flow will be opposite of electron. So current flow exists in this direction. This is the forward current flow. Okay, this is how the PN junction operates here. So conduction electrons have lost energy to immediately combine with the holes in the valence band. What do you mean by this? Immediately when electrons jump from N region to the P region, they often lose the energy here. Okay, and only force that acts here in the electrons in the P region is the attraction force. So electrons themselves, they lose energy when they move from N region to the P region, and now the attraction force will pull the electron and get attracted to the positive terminal of a battery and results in a current called as a forward current. Okay, that's the operation of a PN junction in the forward bias, and the same thing is shown here, as you can see here, without showing the bias voltage. So here electrons, as you can see here, from the negative terminal of a battery, all this pink color region, what we have shown is the electron movement. Electrons are moving to the, because they repel from negative supply and they move towards the junction. And as you can see here, when the electrons arrive here, they lose the energy, and now the attraction force here, positive, will attract these electrons to the positive terminal of a battery, When electrons leave their positions, conversely, the holes will occupy them, and then the whole movement will happen in this direction, in the opposite way. This is the whole movement, and electron movement will happen like this. So this is the electron movement, and this is going to be the whole movement. Okay, and the when the enough number of electrons move from n side to the p side, that can overcome the barrier potential and cause the current to flow from electron current to flow from n to the p, and whole current moves from p side to the n side here. Okay, and all these things has been explained here. The positive side of the bias voltage source attracts the valence electrons toward the left end of the p region. This is what we said here. Okay, the valence electrons are attracted to the positive terminal of a battery of the p region. That's what we mentioned here. The valence electron move from one hole to the next towards the left. When electrons are moving from to the left, okay, that's in this direction. This is the left direction, and this is going to be the right direction. Okay, the holes which are the majority carriers in the p region effectively move to the right side of the junction. As we already said, that holes keep moving to the right side of the junction. The effective flow of holes is the hole current. Okay, as electrons flow out of the p region through the external conductor and to the positive side of the bias voltage source, they leave holes behind in the p region. See, these are the holes left because of electron. Okay, the move from this part of the atom to the positive, and they created holes here. Okay, so that's how the thing works. Let us see the effect of forward bias on the depletion region. As electrons from the n side are pushed into the depletion region, they combine with the holes on the p side. We already seen that. Effectively, reduction in the depletion region happens. This process during the forward bias causes the depletion region to narrow. You can see here in the equilibrium, there's a wider depletion region. This is in the equilibrium without applying any voltage. Okay, no bias, 0 volts applied across this. Okay, so here you have negative and positive. Though it is forward bias, without applying any voltage, we have a wider depletion region here. But applying voltage beyond the depletion region, depletion voltage, which is 0.7 volts, when you apply voltage here, that is shown in the next one. So here the voltage applied is equal to the barrier potential. So what happens, you can see this depletion region has been narrowed here, which has become very thin in dimension. Okay, because of the charge carrier's movement happens from the n side to the p side here. Okay, here we may have a lot of electrons in the equilibrium here. So these electrons, a lot of electrons in the p side, and the holes on the n side. This creates a barrier potential here. When too many electrons move from n side to the p side here, they remove the excess holes here and reduce the barrier potential here. Same thing happens here. Okay, so holes keep attracting towards this, and therefore they fill the electrons present here. So that reduces the barrier potential exist in the depletion region here. Okay, therefore when we apply forward bias, depletion region reduces. Okay, so this is the same thing has been explained here. The students can go through that. The electric field between the positive and negative sides of the junction creates an energy hill. So in order to understand the energy hill, one need to understand the covalent bond formation, and even the different bands exist in the p-type and n-type semiconductor. So if you understand that band, you can understand easily the energy hill. For instance, I think we have a diagram to show that. So let me see here if I have any diagram to illustrate it. Okay, now we have we have only the semiconductor, the band structure. These are the outermost band is the valence band, as you see here, and you have a conduction band here, And when you observe both the valence band and the conduction band of N type and P type semiconductor, okay, so probably here we have, it seems. Let me show you that. Yeah, yeah, yeah. This is what the energy, the hill, what it has been told in the text. You can see here, this is the N type of semiconductor, and this is going to be the P type of semiconductor. The junction, you can see here, this is the PN junction in between. So this is without applying any voltage. As you can see that the conduction band here is lower in the N type compared to the conduction band in the P type semiconductor. So under the diffusion, what happens is these electrons move from conduction band of N region in the, as a diffusion process occurs. They are higher in density. They move from higher region of concentration to the lower region of concentration. So this energy, they may cross, few electrons may cross, and therefore the loses energy and fall into the valence band, as we said already. So now this is what happens under the equilibrium. And now some external force, if it is applied, these electrons can be attracted to the positive side of the battery, and it can create the electron current here. And this is at equilibrium, what happens, as you can see that this is the energy hill established at equilibrium, and some external force raises this, and electron moves from N side to the P side here. Okay, the same thing is illustrated, that is called as an energy hill. Hill means it is a, as you can see here in the band structure, the upper hill has been created here. The height has been increased in the P side, and the electrons need some extra force to overcome that. Typically, the zero point 0.7 volts of external voltage is required to overcome that. And as usual, if you apply the forward bias, the free electrons will get sufficient energy from the bias voltage source that can overcome the barrier potential, and they can climb the energy hill and cross the depletion region. The electrons give up amount of energy equivalent to the barrier potential when they cross the depletion region, and an additional small voltage drop occurs across the P and N regions due to the internal resistance, and that resistance is called as dynamic resistance. The resistance that exists in the forward direction is called dynamic resistance. Of course, it's going to be a small value. Now let us discuss what happens during the reverse bias. So far, we have discussed with reference to forward bias. Any questions in between before I proceed?
No, sir.
Okay, all right. I hope you understood, and let me continue with that. And if you don't have any question, you can also raise a question through the chat, through the chat box. A comment box where you have. You can post it if you have any such. So at last, I'm going to read out those questions and answer you those questions. Okay. All right, let me move on to the reverse bias. Reverse bias is also another type of the voltage that we apply to the PN junctions. We have earlier seen connecting p-type semiconductor to the positive, but now we have seen connected p-type semiconductor is connected to the negative of a battery. Battery has got two polarities, minus and plus, and the minus goes to the n-type p-type semiconductor because we are biasing in the reverse way, and the positive terminal of a battery is connected to the n-type of semiconductor. And look at the internal change, what has happened here inside the semiconductor. It has been expanded, right? The depletion region has been expanded. We will give a clarification why the depletion region has been expanded when you change the bias here. Okay, so when you want to reduce the bias, you must apply in the forward direction. When you apply the reverse voltage here, depletion region expands here, and this type of bias is called as a reverse bias. Okay. So reverse bias is a condition that especially prevents current through the diode. When you want to avoid the current through the PN junction, then you can connect it in this way. Okay, the reverse bias. Okay, what exactly happens in the reverse bias? Positive side of V bias is connected to the N region. Already said about that, and negative side of the is connected to the P region. And depletion region is wider. That's what we need to observe here compared to the forward bias or even equilibrium. Equilibrium, it was a small depletion region of 0.7 volt exist. But in forward bias, which was very narrow, but now the depletion width has been increased. And we'll provide a justification for this, why this depletion region has been increased. And this is the a figure, a diagram that shows a diode connected in reverse bias, and there is a resistor here which is called current limiting resistor. uh, so that limits the current, and the small amount of drop occurs even across the resistor also. So that we'll consider when you treat this diode like a circuit element. Okay, now let us move to the other things, and let us see what happens to the PN junction when we try to bias diode in the reverse direction. So here we need to understand, unlike charges attract each other. We'll see that how this plays a role in the reverse bias. So we have connected here the N region to the positive terminal of a battery, which is shown here, and P region is connected to the negative terminal of a battery, which is shown here. The same negative is brought here, and the positive of a battery is shown here. And now look at internally what happens in the N type of semiconductor and P type of semiconductor. Since electrons, as it is mentioned, unlike charges attract each other. What do you mean by that? Unlike means here the electron in N type, they are the majority charge carriers, and battery voltage that we applied is positive. So that means battery supplies positive charges, and electrons are majority in the N region. Definitely the attraction happens between the electrons and the battery. That means it can attract the electrons from the N region. So electrons, instead of moving towards the junction, electrons will move away from the junction. This is the direction of the electron. Okay. So as you know that when electron leaves the position, what it does, it creates a positive charges, right? So here are all positive charges left behind, and this increases as and when you increase the voltage here. That's the reason here why the depletion width keeps increasing. It keeps growing here. Okay, and same thing happens even to the P side as well, because here you can see that negative battery of negative attracts all the holes present here, and holes are when attracted to the negative part of the battery, that leaves the electrons here behind, and that creates a depletion region here, and this expands when you apply the large reverse voltage here. And because of these reasons, the attraction of unlike charges to the battery happens in both the sides, and this expands the complete depletion region. Okay, any additional holes will be supplied by this. Okay, so these electrons this get attracted to this, and that means it is supplying the holes, in fact, the battery. And here same thing happens, it supplies the electrons, and so this get attract all the holes. Okay, so that's the reason here why the depletion region expands in the reverse bias. And this is a diagram that shows a short transition time immediately after reverse bias when the reverse voltage is applied. And there are a couple of reasons has been given here. In P region what happens, in N region what happens, all those things have explained here. And let's directly move to the current here. The extremely small amount of current exists in the reverse bias. Where exactly current has come from? You can see here now. So far we explained for the majority charge carriers whatever it is happening, but majority charge carriers like electrons in the N region and holes in the P region, they are not contributing for the current because they are moving away from the junction. But what exactly the contributing for the minority current is the electrons here and the holes here. So they are the one which contributes the current in the reverse direction. Why this current is important? Look at here, when electrons are moving away from the junction, what will happen to the electron present in the P region? For them it is forward bias, right? Electrons and the like charges repel, right? So there is negative battery connected here, and the electrons are the minority in number. When I say minority is in number, that creates a small current here. And electrons, instead of moving to the negative of a battery, they try to move towards the junction. They are the minority carriers. This is the electron flow. And look at the holes, what happens here. For holes, the positive of a battery will act as a ripple. It ripples, and the hole will keep moving towards the junction. So this is a movement of holes. That means minority carriers in the N region and P region, they keep moving towards the junction and causes a current flow. If you ask me a question, which direction the current will flow? Current will flow from N to P. Okay, current direction is nothing but the whole direction, we already mentioned it. And look at the direction of holes now. They are moving from N side to the P side. We already seen the forward bias, majority carrier current moves from P to N. And when you reverse bias it, minority carrier current flows from N to P. So this is called reverse current. Reverse current. Reverse current is going to be very, very small. That can be neglected. Reason is it is a current that is flowing due to the minority charge carriers. Minority charge carriers are electrons in the P region and the holes in the N region. They are the minority charge carriers. And that current is going to be very, very small. And same thing we are going to explain here. The extremely small current that exists in the reverse bias after the transition current dies out as caused by the minority carriers in the N and P regions. Small number of free minority electrons in the P region are pushed towards the PN junction by the negative bias voltage. Same thing we discussed. And same thing happens in the N region as well. The conduction band in the P region is at a higher energy level than the conduction band in the N region. We already showed with the energy band diagram. Therefore, the minority carriers electrons easily pass through the depletion region because they require no additional energies. Additional energy is not required for them, so they easily move from uh, different directions as we shown here. It moves current flows from N side to P side, and holes move from N side to P side, and electron move from P side to the N side. Okay, that causes the reverse current as it is shown here. So it is due to the minority carriers. So this diagram shows minority carriers, extremely small reverse current in a reverse biased diode. Okay, due to the minority carriers, and these carriers even sometimes can be thermally generated by electron hole pair happens with the thermally even due to the room temperature as well. And let us see what happens if this voltage is now reverse voltage what we applied is increased. We have seen when the reverse voltage is small what is happening for the minority carrier current, and we have seen for the majority carrier current what is happening. Majority carrier current doesn't exist because the charge are moving up opposite. Minority carrier current exists, but it's going to be very, very small. That's why diode, we say it blocks current in the reverse direction. And now let us see when we increase the reverse voltage to larger value, what happens. So that is going to be called as a reverse breakdown. If the external bias voltage is increased to a value called the breakdown voltage, large voltage applied in the reverse direction is called breakdown voltage, the reverse current will drastically increase. And there are a couple of reasons why the reverse current increases, and we are given that in the following top sections. The high reverse voltage imparts energy to the free minority electrons so that they speed through the P region and they collide with the atoms with enough energy to knock valence electrons in the conduction band. These electrons, minority electrons, they get sufficient energy when you increase the voltage here. Maybe, for example, the voltage between the negative and positive, the reverse voltage, if it is greater than 70 to 80 volts, then that minority carriers here, they acquire a lot of energy and they start colliding with the atoms, other atoms, and tend to release the electrons from them. And that method is called as avalanche effect, which is shown here. Okay, an electron hitting the atom and helping the atom to release the electron. So it is shown here. If one electron knocks only two others out of their valence orbit during its travel through the P region, the numbers quickly multiply. So electrons hitting the atoms and try to release the electrons, and this causes an avalanche effect. From one electron, it releases two electron, 2 to 4 electrons. In this way, electrons will acquire energy and hit the atom and help the atom to release the electrons, and that causes uh, more number of electrons, and that effect is called as avalanche effect. Remember that this happens only when you increase the voltage to 70 to 80 volts in the reverse direction, and this reverse current dramatically increases, and if don't take any further necessary steps to control that current, then it may lead to the large current surge, and it may even damage the diode as well, because this depletion region, it keeps expanding. It only can expand till this and here till this, not beyond that. Okay, and therefore the more and more electrons they keep releasing here, more number of free electrons when we see more number of holes here and more number of electrons here when we see here, then the complete material becomes like a conductor and huge current will flow from N side to the P side, and that causes the device to break down. Okay, so that is the effect of okay, so the reverse voltage, large reverse voltage. Now let us see the voltage current characteristics of the forward bias and reverse bias. So far we explained the operation of what is forward bias and how to connect PN junction in the forward bias mode. And now it's time to look at the graphical plot of the forward bias and reverse bias characteristics. Okay, so here we have a experimental setup to plot the voltage current characteristics of a in the forward bias mode and the reverse bias mode. So here we have two setups, one with forward voltage VF or V bias less than 0.7. This is the setup what we have. And here the second setup what we've shown is a forward voltage overcoming the barrier of this. And look at the notice the diode is shown with a band here. This indicates it is a cathode. And you can see that the cathode is connected to the negative, and here this is an anode side which is connected to the positive, and there is a resistor, and what voltage we apply to measure that, we have a bias voltage, and to measure the voltage across a diode we have a VF. More or less this remains at 0.7 volts, that is the voltage across the diode. But here current keeps increasing when the diode starts conducting. And here this is a setup for forward voltage less than 0.7 only. In this experimental setup, we are not going to apply voltage beyond 0.7. Whereas here, this is in this experimental setup, we apply voltage beyond the 0.7, and we'll see that what is the voltage exist across the diode, which is typically 0.7 volt, which will be there. Okay, and we'll plot this as a graph, and the graph looks like this. Okay, this is the forward bias. Okay, the graph. This is from the first experimental setup. Okay, as you can notice that there are three regions we have observed here. One is A, when the forward voltage is 0, the diode is not conducting, and at the B, as you keep gradually increase the forward voltage, but less than the 0.7, that is the second point B, current is very small, because this height will tell you the current, forward current, which is in milliampere. This is the forward voltage which is along the x-axis, positive x-axis. And where exactly the current starts increasing, this is called the knee region. The moment the forward voltage crosses 0.7, as you can see that there is an exponential increase in the current, and that is nothing but point C. So these ABC points are the important, the one with the no conduction, and small conduction, and large conduction, which is nothing but C. And that is the same forward characteristics when we go in depth with increasing voltage. You can see some linear region here in the in the forward bias characteristics. This is going to be a knee region. Okay, when we vary the voltage in small steps, like delta VF, we can observe the knee region and as well as the linear region. So for the corresponding delta VF, we have a corresponding delta IF is going to be the current. This shows that the small change in the voltage gives you in the early graph, you can see here a large change in voltage, there's small change in the current. But when you go for when the diode is conducting, a small change in the forward voltage makes a big change in the current. That means the current is exponential in nature here. Okay, so this is the observation one we need to do in the characteristics. Okay, so all these things has been explained, so I suggest to students to go through that. And there is a resistance which is important for the students to understand in the forward direction. The resistance is dynamic resistance, because in the forward bias, what is resistance? Resistance is nothing but it is a ratio of delta VF by delta IF. If you take a ratio of this versus this, that gives you the dynamic resistance. Okay, and since voltage is small and current is larger, the resistance value is going to be very very small. Okay, so that is the resistor value is going to be very small. Typically it is 100 to 200 ohm. That's going to be the dynamic resistance. And the reason why we indicate with small r dash d is because r is, whenever we show with small r, though it is a resistance, it is internal resistance here. Okay, it is the internal resistance of a diode. Okay, so therefore we show it with the small r. If any resistance connected outside, it is indicated as capital R. But this is going to be a resistance which is seen inside a diode. Therefore, it is internal resistance. Therefore, we show it with small r dash d. D indicates it's a dynamic resistance here. So whenever diode is conducting, so we have a resistance that can be measured by knowing the change in the value of forward voltage to the change in the value of forward current. Okay. Similarly, we can also show the reverse bias characteristics when the diode is connected in the reverse. We already shown circuit setup and earlier how to connect it in reverse bias. Now we have to observe the current flow in the reverse direction. So as we said already, until you go to the breakdown voltage, VBR indicates the breakdown voltage, and you can see the curve is falls in the third quadrant. Like in the forward bias, we have seen in the first quadrant, because both voltage and current are positive, but here voltage and current are negative. So therefore, it falls in the third quadrant. And you can observe here when the initially when the reverse voltage is increased, okay, due to the minority carrier current, as we said, it is going to be very very small. So you can see curve is the blue color curve. What you have seen is very close to the x-axis. This will tell you the height here, will tell you the current here. So since it's overlapping with the closely overlapping with the x-axis, the reverse current IR, what we say, it is going to be very very small, because majority carriers are moving in opposite direction and minority carriers are moving towards the junction that causes the minority carrier current. And this happens till you reach the voltage breakdown voltage. When VR is exactly equal to breakdown, look at what happens here. So the sudden surge in the large number of electrons are acquire energy, and as we said, the effect called as avalanche effect, that makes the creates a lot of electrons in the P and N type semiconductor, and that causes huge current to flow. That means it's a condition when which diode will is in the verge of the damage or breakdown or whatever you call. So diode is going to be damaged when the large amount of current flows. It becomes like a conductor. That's why you see large amount of current here. Once VR reverse voltage crosses VBR. But to be safer side, when reverse voltage is within VBR, you will get small amount of current and diode is not damaged. But the moment you cross when the reverse voltage crosses VBR, we see huge surge in the current flow that causes huge current flow and damage of the PN junction itself here. And so we have a typically voltage greater than 50 volts or 70 volts that causes breakdown. That depends on the data sheet. Okay, so data sheet of a diode manufacturer provides always what is the breakdown voltage. Okay, typical breakdown voltage, though it is mentioned here 50 volts, generally it goes from 50, 75 volts, 80 volts, something like that. Okay, so ordinary PN junction diode, once it is operated in the reverse region, it breaks down here. Okay, and now to understand complete the characteristics, we have both forward bias and the reverse bias shown in the single graph. Students are expected to, whenever they ask in examinations, to write explain voltage current characteristics of the PN junction, are expected to write this one. You may also explain individually first in the forward, as we say, shown with less than 0.7 and greater than 0.7, how it affects the forward current. You can also show that, and later on you can consolidate into this kind of the graph. And as usually here, this is a forward voltage, and this is going to be the forward current, and the curve is in the first quadrant. So this is going to be the forward bias characteristics. When VF is 0, current is 0. When VF crosses 0.7, the barrier potential VB, then there is a huge surge in the current here. And look at the reverse direction. What happens when the reverse voltage, the VR is less than VBR, you have a very small amount of current here. And when VR, reverse voltage, crosses VBR, then there is a huge surge in the current, and the device will break down if you continuously operate in the reverse direction. Okay. And to see understand the temperature effect, we have here a couple of graphs which are shown here. What happens to the PN junction when you operate it in the higher temperatures with forward bias and higher temperature in the reverse bias. Here the blue color shows the normal room temperature characteristics, which is 25 degrees Celsius. But the pink one shows when the temperature is increased by delta T. So what happens here? Okay, in the forward characteristics, you can see that here the current starts increasing as temperature is increased, and forward current also starts increasing for a given forward voltage. That's why the curve is very close to the y-axis. Further, if you increase the temperature, you may get a curve something like this, something like this, like this, like this. As we keep increasing the temperature, curves will move towards the y-axis. Okay, that is in the forward direction. What happens in the reverse direction? So curves will be moving away, I mean towards y-axis again, but it is below the normal diode, as you can see here. Okay, so the generally we can arrive at standard rule. The barrier potential decreases by 2 millivolt for each degree increase in the temperature. For every degree increase in the temperature, there is a barrier potential drop by 2 millivolts. That's in the forward direction. Whereas in the reverse direction, as temperature is increased, the reverse current increases. Okay, there's a difference here, as you can see, the key difference between the forward and reverse curve. And we need to keep in mind that the reverse current below breakdown remains extremely small and can usually be neglected here. This current, what it is shown here, can be neglected below the breakdown. Okay. So any questions so far? You can feel free to ask in between if you have any doubts before we move to the next one. Another 5-10 minutes, we'll just wind up this class. Okay, now let us move on to the rectifiers. This is a typical application of a diode, which is half-wave rectifier. We already know that diode conducts in one direction, blocks current in the other direction. The major application of diode is the rectifier circuit, which converts a circuit which converts AC voltage to a DC voltage. So AC voltage is required for the bulk, electrical applications, but DC is required for the small electronic applications, especially the laptop, mobile, any small applications like desktop, or today's scenario. If you ask me, there's a LED TV which requires DC voltage instead of AC voltage. Okay. Now, question is now how do we get DC voltage? So even the electricity supply companies provide AC voltage for us, but we need to have an adapters. Within that, you see a DC power supply that converts AC to DC. Generally, DC voltage you can get it through the batteries, or it can be converted from an adapter from AC to DC. Okay, there's no other options for us available. Now, question is now how do we convert AC to DC when the AC voltage is available? So first block is the rectifier block. We'll discuss that in detail. And before that, before we discuss the rectifier, let us go through the various blocks of DC power supply. To generate a DC power supply, what are the various blocks we need? Assuming that we have with us an AC source, okay, how do we convert AC to DC? So we have a basic DC power supply block diagram. And here we assume that North American standard, which is 120 volts AC and 60 hertz is the frequency of AC supply available with us. In India, it's going to be 220 volts AC voltage, and frequency is going to be the 50 hertz. And here this textbook follows North American standard, so therefore we need to work with all our AC voltage source having has a 120 volts of magnitude, and 60 hertz is going to be the frequency at which AC wave moving. AC means you can imagine it is a sine wave, nothing else like this. A sine wave which oscillates at the frequency of 50 hertz and 220 if it is the Indian standard, and if it is North American standard, it's 120 volts. It's a peak, positive peak, and the frequency is going to be 60 hertz. And now DC voltage is required in majority of applications like consumer electronics and computers, industrial controllers, laboratory instrumentation systems, and many equipments require a DC voltage. But often we have AC voltage available because to avoid losses happens, in the transmitting AC. DC cannot be transferred from one point to another point because of huge copper losses. So, but AC can be transferred from one point to another point. And this is a block diagram of the DC power supply. We have a transformer in which we give an AC signal for that, and transformer converts step downs the AC voltage. The transformer is used for multi-purpose. This can step up, it can step down, it can even provide equal voltage AC voltage. This doesn't convert AC to DC, but it gives you AC input. It will step down to AC itself. So if it is North American standard, the input what we provided is 120 volts and 60 hertz. Here, it may be converted to, say, for example, 15 volts and 60 hertz. Frequency remains same, but magnitude has been reduced. AC voltage from 120, it can be brought down to 15 volts or 10 volts, because the electronic circuits which is ahead of us, that needs a small voltage. Straight away we can't give 120 volts or 220 volts to the circuit, which is electronic components which exist in these circuits. So rectifier, which is a preliminary block in the DC power supply, which converts AC wave, which is a full cycle, into the partial cycles like this. If it is a half wave rectifier, and negative cycles are suppressed here. You can see here there is no negative cycles here like this, which has been suppressed by the half wave rectifier. If it is a full wave rectifier, you get all positive cycles here. And filtered output, the filter is again to smoothen the AC signal coming out from half wave or full wave. We need a filter circuit which will smoothen this fluctuating AC wave. We need to get a DC voltage which is of constant like this, and that is possible through the regulator. And finally, we have here some application which needs a DC voltage connected to the regulator. And the role of regulator, role of filter, role of rectifier is very important in deciding the what percentage of AC we converted into the DC. Okay, so that's very important for us. Okay, so that's about the circuits. Probably in next class we'll discuss about the online class. We'll discuss about rectification and other rectifiers. I'll stop at this point, and now the platform is open for any questions and answers. Any questions are there? You can post even questions online. I mean, in the chat box. Okay, so you can answer them. Or if you wish any topic to be discussed in the next class, also you can just mention it so that we can cover up in the next class. I hope you all got some information or knowledge with reference to the PN junction or diode. Any questions? Any topic which you need explanation?
Sir, as we saw that output of the diode changes with the temperature, so how we cooperate with it?
Come again. Diode operation changes with temperature. Correct.
So how in electronic devices like laptops that heat a lot, how we cooperate with that?
Yeah, because the major problem with the PN junction diode is the temperature variations. We already seen that whenever room temperature exceeds in the forward direction, and just go to the respective graph to show you that how temperature varies and its effects forward. This is what the curve we have shown. So in today's scenario, no, we don't use PN junctions in most of the applications. Maybe you are asking me about laptop or the mobile phone or whatever. Generally, we use transistors in place of PN junctions. Uh, though the PN junction is embedded inside the transistor, the working principle of transistor is almost same as the PN junction. But there are multiple junctions, of course. If you take bipolar junction transistor, there are two PN junctions within that. But we don't use even bipolar junction transistor in today's applications. We use MOSFETs and CMOS transistors in today's laptop and mobile phone applications. Probably a mobile phone has got a few millions of transistors, MOSFETs, and desktop or processor used in the desktop has got few billions of uh, transistors, which is typically a CMOS transistors. We don't use diodes in the those high-end applications. We generally use what is called a CMOS, which consists of NMOS and PMOS. These are the basic elements in the today's a laptop or mobile phone. Okay, which is functioning within that as a switch uh, application. Okay, but as I said that the diode keeps varying the temperature, but they're all insensitive to the temperature. Not too much variations we can see in the CMOS device when you operate at higher temperatures. Of course, the performance affects the temperature, but not like as you see in the diode. But diode is very sensitive element, and a lot of power consumption happens when the temperature varies. That's the reason here we don't use diode in majority of the applications. But we can't ignore diode because diode serves as a basic function in understanding of CMOS. Okay, so from the diode, the concept of diode should be understood before we go to the concept of CMOS. Okay, but of course the temperature varies in this way. What it is, the way we have shown here, the graph, it affects as temperature increases, the currents also starts increasing. So these are the devices which are sensitive to the temperature. Okay, I hope I've answered your question. Any other questions here?
No, sir.
All right, then if you don't have any questions, let us wrap up this today's session. I hope this session uh, is useful to you, and next session will explain you on the rectifier circuits, which is very important, circuit which converts AC to DC. Probably in the next Saturday or Sunday, we'll take up even rectifier circuits as well. Okay, thank you all.